Thank you, Leah. So, yes, what I'm going to be talking about today is sort of about and maybe more around a result I recently proved with Jakob Stix from the University of Frankfurt, which is what the title alludes to here. And I guess sort of my aim today is not necessarily to really go into the details of the proof in any way, but more to sort of give you a bit of a sketch of the sorts of areas of modern number theory which our work was sort of touching on, and sort of give you an idea of the geography of at least some parts of number theory at the moment. And sort of the whole setup for this problem that we were thinking about comes in an area known as Abelian geometry, which is what I'm going to talk about for the first 20 minutes or so. So the story of Abelian geometry, this is an area of number theory, and it dates back to a rather important year, 1983, which we've already seen in Leah's talk mentioned as the year in which Faltings published his paper Ähnlichkeitssätze für abelsche Varietäten über Zahlkörpern, which is where he proved the Mordell conjecture and the Shafarevich conjecture for abelian varieties and many things. But also in this year, shortly after Faltings proved that, Alexander Grothendieck wrote a letter to Faltings in which he proposed an alternative way of trying to address Mordell-type questions, which was this Abelian program. And I guess by this point, Grothendieck was already kind of well into the mode of trying to think, and everyone was well into the mode of trying to think of solutions, like trying to solve equations as trying to find points on certain kinds of like shapes, varieties in kind of proper language. And I guess the sort of thought that was going around Grothendieck's head was, well, if we just talk about normal topology, we actually have a whole suite of tools for studying topological spaces coming from algebraic topology. So things like fundamental groups, cohomology groups, and so on. And what Grothendieck wanted to be able to do was to also study varieties, that is, study systems of equations, by using sort of topological tools. And in the Abelian program, he was specifically interested in studying Diophantine geometry via fundamental groups. So you probably all know what a fundamental group is, but I will at least give a very kind of quick definition. So this board here is going to be not number theory, it's going to be actual algebraic topology. But this pen is better. So if X is a connected topological space, then its fundamental group, I1 of X, this is just the set of loops in X, where we think of two loops as equivalent if they can be sort of continuously deformed into one another. So this is a sketch definition, if you like. So loops modulate continuous deformation. And if I'm being really very careful, I should actually choose a base point in X and say that, like, base loops. I'm going to not talk about any base point issues today because they're always tedious. So some examples of what this actually looks like. So if X is the surface of a sphere, which is notoriously hard to draw. Well, you can kind of convince yourself that if I have a loop on the surface of a sphere, I can always like shrink it down to the south pole, for example. And so in fact, for the sphere, you can rigorously prove this as well, the fundamental group is the trivial group. I should have said there's a group structure on this given by composition of loops, but we don't need to worry about that too much. So for a second example, maybe X looks like the surface of a donut. And on the surface of a donut, there are some obvious loops, like there's, you can take this loop kind of going around here like you were cutting a piece of string, or you could take this loop going all the way around here, like you're cutting a bagel in half. And And in fact, neither of these loops can be shrunk down to points. These kind of give you genuine non-identity elements in your fundamental group. And in fact, what the fundamental group here is, it's the free abelian group on two generators, also known as Z squared. And these are actually the generators. And a kind of third example. So maybe X looks like a donut with 2 holes, or maybe a donut with 3 holes or 4 holes or something. Basically, X looks like some sort of accident in the Dunkin' Donuts factory. G holes at least 2. Then your fundamental group here is it's a bit complicated to write down, but it's generated by 2G different elements, usually called A1 up to AG and B1 up to BG, modulo one relation, which I'm not going to write down. And one thing that's actually very different between these three different cases is that these two fundamental groups, the trivial group and Z squared, these are abelian groups. And this group here is always non-abelian for G at least 2. So this was the theory which Grothendieck wanted to import into algebraic geometry. And it's very much unclear how you're supposed to do this, but Grothendieck did manage to do this. He managed to define for any variety, so any sort of shape defined by some system of polynomial equations, something that he called the étale fundamental group. And there's a small issue here that another issue I'm going to sweep under the carpet, which is that this is not a usual discrete group like this. They're actually they carry topologies on the group itself. They're profinite groups, but that's not necessarily important for like, getting the idea of what I'm talking about today. And as I say, so Grothendieck came up with some definition. What does that definition actually look like in some practice? So there are kind of two examples are worth bearing in mind. And the first is, okay, so maybe the space I'm studying is a connected variety over Q bar. So it's something defined by some system of polynomial equations with coefficients which are algebraic numbers. Well, in this case, you can look at the solutions to your equation over the complex numbers. That's what this y bracket c thing means. I can just use the actual pointer. There we go. And this is some topological space. This is the analytification which Jackson was mentioning yesterday. And you can actually look at the actual fundamental group of that actual topological space. And it turns out that this étale fundamental group that Grothendieck defined is just giving you the same thing as this topological fundamental group. Again, modulo something to do with profinite stuff because there's a hat there, but ignore that. But the second example is maybe much more interesting for a number theorist. So one variety that you have is, in some sense, the most boring variety, which is like the variety which just is a single point. If you like, this is the variety defined by no equations in no variables over K. But this gives you some well-defined variety. And you can look at its étale fundamental group, and it turns out this thing is actually giving you the absolute Galois group of your field. Okay, so we kind of know what's going on for this kind of the spectra of a field. We also know what's going on for varieties of algebraically closed fields. And it turns out that in general, a fundamental group of a variety is sort of a mix of these two things. So I'm probably not going to go through exactly the details of this construction, but if I take a variety over a field which is not necessarily algebraically closed, then okay, I can use the language of exact sequences here, but this fundamental group of Y, this sits in the exact sequence mapping onto the absolute Galois group of K, and with the kernel being the étale fundamental group of the base change of Y to K bar. So this is like a topological fundamental group. This is like a Galois group. And if you don't know what the word exact sequence means, I can say this precisely. It means that there's a group homomorphism from the fundamental group to GK. And this is surjective, and its kernel is this topological fundamental group. So the sort of idea is, for a variety over a field, its fundamental group is like a mixture of a topological fundamental group and a Galois group. And yeah, this sequence is often known as the fundamental exact sequence. And Grothendieck's idea was that one can use this fundamental exact sequence to try and study the rational points on Y, that is, the rational solutions to the system of defining equations. And the way that this works is, okay, I guess I've set up here how you do it officially, but just what's you, so to every single rational point on Y, you can associate a splitting of this exact sequence. That is to say, a right inverse to this map. So a splitting of this exact sequence is just a map from GK to fundamental group, such that if I do that map and then back to GK, then I get the identity. So yeah, so we have I've just given a name to this thing. I've called this thing the section map. So to every k rational point, I can associate a splitting of this fundamental exact sequence. And the big conjecture which Grothendieck originally formulated and still remains very open is known as the section conjecture. And so Grothendieck said, well, yeah, so if my field I'm working over is a number field, which it will be for the rest of today, and if this variety I'm looking at is a smooth projective curve of genus at least 2, then he said that this section map here from k rational points to splittings of this sequence should be a bijection. And what this should be telling you informally is, so this right-hand side, the section set, this is something which is just determined by the fundamental group of Y. So the slogan here is basically, for smooth projective curves of genus at least 2, the fundamental group determines the rational points. Or at least it should. This is what we believe to be true. And you'll recognize this genus at least 2 thing as kind of a common theme through many of the early talks. So maybe to give you a little bit of context about what do we actually know about this conjecture? I said it was kind of very open, but so I guess the first thing to say is, well, if you want to prove that something is bijective, your first thought is, well, I'll prove it's injective and I'll prove it's surjective. And already when Grothendieck wrote his letter to Faltings, he included in that a proof that this section map is injective in this setup. So the question at play is whether or not it's surjective. It turns out now with, I guess, just slightly under 40 years of experience as a community, the surjectivity part is really hard because it's effectively asking if I give you some splitting of some sequence on fundamental groups, like, can you produce me a rational point on a curve? And the thing is, we don't have actually very good methods for producing rational points on curves. We can like write down some equations and write down a solution to those equations, but we don't really have any other good techniques for doing so. So that's kind of why this is maybe quite a hard question. But we do actually know a couple of examples where this section conjecture is true. And this was the first examples were constructed by Jakob, but there was a more recent one by Wanlin Lee and Daniel Litt, Nick Salter, and Padma Srinivasan. And in all of those examples, what you do is you construct some curve where you can show that this fundamental exact sequence that you had doesn't have any splittings at all. And then, well, this section map is a map to the empty set, so it's going to have to be bijective. But it's worth saying that these are the only examples which are known. If someone says to me, can you give me an example of a curve which has a rational point and the section conjecture holds, no one knows the answer to that. But kind of for today, maybe the relevant thing to talk about is the third thing, which is more about the history. As I said, this was formulated in a letter to Faltings, in which Grothendieck said that it would kind of propose this as an approach to giving a new proof of the Mordell conjecture. And so this is sort of like a load of thoughts which were kind of swirling around my head when I was starting off my PhD. And one sort of question that seemed quite natural to me, which other people have also thought about, is the following. So if you believe the section conjecture, so sections is the same as rational points, and if you believe the Mordell conjecture, you should because it's a theorem, then you certainly believe that this set of sections should be finite. And what I was interested in is, can one actually prove this unconditionally without assuming the section conjecture? And the answer is I still can't prove that. But I can say something kind of in this direction. So I'm going to take, sort of at least give you a statement of the theorem that we proved. And in order to do that, I'm going to introduce a certain subset or variant of this section set, which is actually quite, when you see certain, it's quite natural from a number theoretic perspective. These sorts of constructions appear quite a lot. So we should draw the fundamental exact sequence again, just to remind you. So okay, so we're in this, we're looking at the fundamental group of a variety k bar. I should probably have said if you want to say k equals q, please do. So this lands in the Galois group, on the right-hand side. And contained inside the Galois group, I guess this was covered in one of the courses earlier this week, contained inside here, you have the decomposition group at every place of your number field. Place kind of just means prime-ish. So if you're only happy with primes and number fields, then replace place with prime. So I was writing those. This is the same thing as the absolute Galois group of the completion of your number field at that place. And this is the decomposition group. And so in particular, if I have a splitting of this exact sequence, so it's a map of groups in that direction, I can just restrict it to this decomposition group. And when I do that, what I get is I, in fact, get a splitting of this exact sequence, which is the same fundamental exact sequence, but for y viewed as a curve over the completion of k at v. And so you can ask, so I have this section of the original fundamental exact sequence, I restrict it, get a splitting of this sequence, and I can ask, does this splitting come from a kv rational point 1 dot? And if it does, for every single place v, we call this section Selmer. This is some niceness condition on sections. And so what we've effectively done, is we've just sort of cut out a nice subset of the whole section set. And one of the reasons this is nice is that this weird Selmer condition that I've written down is automatically satisfied for every section coming from a k-rational point. So this sort of sits between the two. And actually, this is kind of quite a, if you dream of proving the section conjecture one day, this is maybe quite a natural way to try and approach it. You want to show that these two sets are equal. Well, maybe you show that every section is Selmer, and then you show that every Selmer section comes from a k-rational point. Not to say that either of those are actually easy, they're not. And to just sort of fix a little bit of notation, I said this, if I have a section then which is Selmer, then its restriction to every decomposition group needs to come from a local point yv. I'm just going to denote this this point yv by loc v of s, just so that I can think of this as a function from Selmer sections to kv points. And later I'm going to parcel this all together into and think about all of these localization loc v maps simultaneously as defining a map from the Selmer section set to the product of all the local points. And this is, if you've met Adels before, this is called the Adelic points of y. And I wouldn't worry about that too much. Just the next theorem only talks about loc v. So this is the theorem that we managed to prove. We need one assumption, which is that our number field k contains no CM subfield. So I probably should have just assumed k equals q for the whole talk. But we do actually prove this over some other number fields. But under this assumption, then no matter what curve you give me of genus at least 2, and no matter what finite place you give me, what prime you give me of k, the image of this Selmer set under this localization map is finite. And okay, if you squint, you can at least convince yourself that this should be a consequence of the section conjecture, even if you forget most of the definitions. This is a subset of the section set, and so if the section conjecture holds, then the whole section set is finite. So this subset is finite. So its image under this map is finite. But the point is, we do actually give an unconditional proof of this. And so I'm going to say something about not exactly the proof, but sort of the way we like to try and think about what we're trying to do here. And this is going to take a bit of a swift pivot to something apparently unrelated, which is called obstruction theory, which is also like a thing that people study a lot nowadays. So I think I might see who's awake. So let's do a couple of quick Diophantine equations as a warm-up. So I'm going to do it work over Q. So let's think about, so we're trying to solve these equations in rational numbers. So here's a nice, easy warm-up Diophantine equation. Let's try and solve the equation x squared plus y squared equals -1. Any takers? Yes, I see a 0 being held up at the back. Yes. So so there are no solutions at all. In some sense, there are no solutions because x squared and y squared are non-negative, and -1 is not. But a slightly more refined way of putting this is, well, if x is any real number, then its square is still non-negative. If y is any real number, then its square is non-negative. So in fact, this equation doesn't just have no rational solutions, it has no real solutions. So in fact, it has no solutions in the real numbers. Okay, now let's go for a similar looking but slightly different equation. Let's go for x squared minus 3y squared equals -1. How many solutions do we have here? If you want to start solving it over integers, that's also fine. Yes? Yeah, mod 3 and see what happens is a good idea. So if you're looking for integer solutions, then mod 3, this is the equation x squared equals -1. And -1 is not a square modulo 3. So there are no integer solutions to this equation. And if you're slightly more careful, you can do this also for rational solutions. So again, it turns out there are no solutions basically by thinking modulo 3. And I'm going to again put this in a slightly more refined way. I guess you saw in your local fields course that you have these fields QP, which contain the rational numbers. And this argument about reduce modulo 3, blah, 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 works just fine over in Q3, the completion of Q at the prime 3. So in fact, this equation has no solutions in Q3. So this is kind of one way you can show that equations have no solutions. I'm not going to ask for volunteers for the next two equations, because that would be mean. So here's an example of an equation. 2y squared equals x to the 4 minus 17. And so this is a curve which was studied by two mathematicians called Lindt and Reichhardt. Or I might ask for think about solutions to the equations, the rather nice looking equation, 3x cubed plus 4y cubed plus 5z cubed equals 0, and I'll exclude the obvious solution. So non-zero, not all 3 equals 0. And this equation was studied by Selmer. And to cut a long story short, both of these equations don't have any solutions over the rational numbers. But these sorts of approaches will never show that these equations have no solutions over the rational numbers. So this equation does have solutions in the real numbers and in QP for all P, and similarly for Selmer's equation. So obstruction theory is really the study of somehow like how can things like this occur. So good. Just my handwriting. Obstruction theory is kind of concerned with the question, how can it occur that the set of KV rational points on Y is non-empty for all places V, which over the rationals is just saying no solutions over R and no solutions over any QP. But still, the set of but still there are no rational solutions. And I'm just going to also slightly rewrite this condition, saying that these sets are non-empty for all V is actually the same thing as saying that the product of all these sets is non-empty. And more generally, I guess this is usually how obstruction theory is formulated, but you can also kind of ask more generally. Wrong pen. How does the inclusion, so the rational solutions to your equation certainly live inside the KV point, the KV solutions for every V, and in fact, the rational solutions to your equations land inside this funky product of all the local solutions. And in some sense, obstruction theory is a question about what does this inclusion look like? And this is a very, very vaguely and probably badly formatted question, but maybe I'll sort of illustrate this with an example, which shows you how you can actually say something about where these rational points lie inside this weird object, this product of all the local points. And you can do this using the theory of étale cohomology, which again is sort of actually quite similar to this original Abelian program. This is like an analog in the world of varieties for like singular cohomology of topological spaces. And I'm definitely not going to give you a definition, but sort of the quite surprising thing about étale cohomology, and the thing that's very useful for number theorists, is that these cohomology groups aren't just some like random abelian groups. They in fact always come with Galois actions on them. So these are giving you Galois representations, which was it Keith talked about last week? The person who's being pointed at talked to Alvaro. Okay, yes. And so the way that you can actually use étale cohomology to study rational points is some variant of the following game. So you want to take a smooth, proper family of varieties, that is to say, in proper language, a morphism of varieties which is smooth and proper. And you want to think about this. So this is, let's draw a sort of cartoon. Here's X. It's some sort of space. Mapping down to Y, also some sort of space. And so in particular, to every point in Y downstairs, I can look at its fiber, that is the set of all points in X which map down to it, the pre-image. So if this is the point Y, this fiber is usually denoted x sub y. And so I can use this construction to associate to every point in y a Galois representation. Namely, I want to take the fiber of this family over that point and look at its étale cohomology. So I've got some recipe which associates to every point of y a Galois representation, or more precisely, every k-rational point, a representation of the Galois group of GK. And if I take okay, I've said a Delic point here, I probably shouldn't say that. If I give you a point, a kv point, yv for each place v, then I get a bunch of local Galois representations of all the decomposition groups at every single place of my number field. And you can ask yourself the question, does this big bunch of local representations all come from a single global representation or not? Which is, I guess, what I've written formally there. And so we just, as a definition, we'll write, I'm using Delic points now. We'll use a subscript x to denote the set of tuples of points yv, one for each v, such that all of the associated local representations are interpolated by a sort of single global representation. And whatever it is, the final output of this definition is I've managed to isolate a certain subset of the adelic points of y. That is the product of all the local points. And again, much like in the sort of section conjecture story, this set I've managed to construct here contains the k-rational points. So this, in some sense, this thing in the middle is saying something about where the k-rational points lie inside the adelic points. And in particular, we can sort of find some reasons why equations might have no solutions. So maybe I managed to find some variety where, okay, there are adelic points. This set here is not empty, but maybe this intermediate set is empty for a particular choice of smooth proper family. And in that case, well, the emptiness of this implies that that set is empty. So in some sense, when this middle set is empty, you have a good explanation for why there are no k-rational points. And I'm not sure if it's necessarily of this shape, but certainly obstructions which look like this can actually be used to explain why this equation and why this equation don't have any solutions. That's like a sort of broad strokes overview of what is meant by obstruction theory. And why is this actually relevant to what I was talking about? Well, I'm going to not talk about any details, but some other the point is actually inspired a little bit by topology. So in the world of topology, you can do the same thing. You can have like a morphism between a continuous map between some topological spaces, and you can look at you can just look at the singular cohomology of this fiber. And one thing that's rather, one thing that you learn in topology is that if this map from x to y is suitably nice, then these cohomology groups, as you vary your point y in the base, they vary continuously. So these vary continuously with the little point y. And here, you have to actually pin down what that means. If you want to be very proper about this, use the word local system. And again, so you vary in a local system. And again, something that you learn from algebraic topology is that local systems on a topological space are, for nice topological spaces, equivalent to representations of its fundamental group. So in the world of topology, if I have a suitably nice morphism of topological spaces, I can actually use this to get a representation of the fundamental group of the base. The same thing happens in algebraic geometry, and the real words are there. But the observation that I think is quite interesting is, so we've got this smooth proper family we're thinking about in the world of obstruction theory. So we get this representation of the fundamental group. And so if I have a section of this fundamental exact sequence, which I was there and then I erased, well, the section is in particular a group homomorphism from the absolute Galois group to the fundamental group. So if I have a pi1 representation, I can just sort of forget all of the pi1 action except the GK action to get a GK representation. So this kind of very nice construction which takes this local system or this smooth proper family and associates to every section of this fundamental exact sequence a Galois representation. And it turns out that when this section was chosen to be Selmer, this nice condition I talked about earlier, then the associated local points have to be unobstructed by this this smooth proper family. So this is like the connection between, on the one hand, this Selmer section set, and on the other hand, this like obstruction theory picture. So there's just like a slogan that these kinds of obstructions actually don't just constrain rational points, they also constrain this mysterious Selmer section set that we want to study. And so, so in fact, I think you've sort of seen various versions of this conclusion earlier. So like if we ignore this term here, this was just the inclusions I had earlier. So the k rational points live inside the adelic points, and in fact they live inside this obstruction locus coming from this family. And what I'm saying here is that in fact, between this obstruction locus coming from this family and the k rational points, somewhere lies this Selmer section set. And so then I guess you can probably see the function line of how you might prove a result like Jakob and I did, is you find a very good obstruction, which allows you to say something about the finiteness of this set. And I'm really not going to have any time to say anything sensible about this, but then again, I didn't actually plan to. But to sort of like maybe make a connection to something much more recent, the obstruction that we use in order to get this is an obstruction that essentially appears in a paper from 2020 by Brian Lawrence and Lawrence-Venkatesh, in which they give a new proof of the Mordell conjecture. And okay, their paper isn't actually explicitly written this way, but their argument is essentially an obstruction theoretic argument. And so so what they're doing is, rather than considering any old smooth proper family, they consider smooth proper families of a very special shape. And now I'm definitely, in the last 5 minutes, going to start using a few more unexpected terms. But yeah, they consider these sorts of smooth proper families you get by taking first a finite covering of your curve, and then what's called a polarized abelian scheme, like a sort of a family of higher dimensional elliptic curves, if you like. And this means, to cut a long story short, that not only do you have these representations you can associate to every single point, but these are kind of structured representations. Like, we know that cohomology groups carry like this cup product operation. And so, for example, zeroth cohomology should always be an algebra because it has this cup product takes H0 and H0 to H0. And H1 is always some kind of module over H0. And this word polarization tells you there's some kind of like antisymmetric pairing on the bilinear form on this space. And okay, it doesn't really matter what all these terms mean, but you get these very structured kinds of Galois representations, and you can form exactly the same sort of definition of an obstruction locus as I was talking about earlier, except you want to pay attention to all these extra structures lying around. But long story short, we define an obstruction locus using this Abelian-by-finite family. And what's kind of amazing about their proof is that, unlike every other obstruction I know, it's actually enough to say something about about finiteness. And so, in fact, what they prove, you need to actually do quite a lot of extrapolation for what they prove in order to get this. In particular, there are various steps to the argument that need to be generalized. But yeah, if you're in the special case where your field K contains an OCM subfield, then you can actually always choose your Abelian-by-finite family to make the projection of this obstruction locus on the KV rational points finite, and then that just implies the theorem that I said earlier. And okay, I actually just wrote that there. But yes, I think I will leave it at that with 20 seconds to spare.